spring break starts, so I consider this quite a nice handout for that. So we're very fortunate today to be joined by Chris Scarvelis, who's a PhD student at MIT, who's part of Justin Solomon's group, and works on interesting questions in understanding how generative models work, particularly how diffusion models work. And so we're going to hear a little more about how these tools that most of us are using in a lot of our research actually do what I'm very curious. So take it away.
All right. Thank you so much for the warm welcome, Daniel. I really appreciate it. Thanks all for coming out today. So good afternoon. As you all now know, my name is Chris Scarvelis. I'm a final year PhD student in Justin Solomon's group at MIT. As of 14 hours ago, I'm also incoming faculty at Rutgers. And thank you. And I work on the foundations of generative AI. I'm particularly interested in how generative models are shaped by their training data, and I'd like to spend some time with you today exploring that relationship through the lens of diffusion models. So before getting started, I just want to say a bit about my professional background. I did my undergrad in math and economics in McGill in Montreal, where I worked on problems like blind deep blurring and fair short division. I then begun my PhD in Justin Solomon's geometric data processing group at MIT in 2020. Over there, I first worked in optimal transport before my research interests evolved towards generative AI. We're an eclectic group. My colleagues work in domains ranging from graphics to Gen AI, but the common thread in our work is that we're all interested in geometry. Now, for some of us, that means the 3D geometry of shapes. For others, like me, that's closer to the infinitesimal geometry of probability distributions. During my PhD, I've done research at Twitter, where I worked on graph neural nets, Backflip AI, where I worked on 3D deep learning, and at IBM, where I worked on model merging for LLMs. And so if any of those topics interest you, I'd love to chat about them later. But before that, let's talk a bit about data dependence in diffusion models. All right. So generative AI has recently achieved some truly surprising breakthroughs. For example, ChatGPT has recently solved an error problem nearly on its own. Systems like Gemini generate photorealistic images of scenes that could have never existed. And systems like Boltz generate new molecules that are tailor-made to bind to biological targets. These are all instances of sampling from a probability distribution, and we made rapid progress over the past decade by reframing the challenging task of learning a probability distribution as different types of supervised learning problems. So for instance, training a language model nowadays amounts to solving a classification problem called next token prediction. And on the other hand, training a diffusion model entails solving a regression problem called score matching. We're going to say more about this problem soon. Now, this paradigm has been very successful in practice because it's allowed us to deploy the well-developed machinery of supervised deep learning to solve generative tasks. This includes neural architectures like U-nets and transformers. It includes training procedures like gradient descent. But it also includes a large body of intuitions about how to solve supervised learning problems via deep learning. These intuitions reflect best practices that we mostly take for granted nowadays. But there's one intuition in particular that fails badly if we try to apply to generative modeling. So because supervised learning problems are typically underdetermined, it's possible in principle to perfectly fit the training data, but also generalize well away from it. In particular, that's what the ground truth function does. Now, this also happens in reality, and it's standard practice nowadays to seek models that drive their training loss to zero, because it turns out that these often generalize better than if we try to explicitly avoid overfitting. Theories like double descent and grokking, which you may be aware of, are attempts to explain how and why this works. Now, on the other hand, this cannot happen in generative modeling. The supervised learning objectives that we use to train generative models have single solutions. And if we reach them, we get models that can only generate their training data, which isn't useful in practice. This leads us to a dilemma. If we followed our intuitions from supervised deep learning and just driven the training loss to zero, the relationship between the samples our generative model creates and its training data would be trivial. Every generated sample would correspond to a training sample. We could easily predict what samples this model might create just by looking at its training set. And this model would be useless to us precisely because it depends trivially on its training data. On the other hand, real-world generative models succeed at creating new data, but this is only because they depend on their training data in a complex and opaque manner. Because generative models have been so successful in practice, we have a pressing need to understand the real-world behavior. And to do this, we therefore need to understand the relationship between generative models and their training data. That is the overarching goal of my research. To understand this relationship, we need to understand two phenomena. The first is generalization. How and why do generative models generate new samples rather than simply memorize their training data? The second is data attribution. How does a particular generative model's behavior depend on its training data? And how does behavior change if its training data were different? So far, I've worked towards understanding this relationship for diffusion models, which are standard tools for tasks like image and molecule generation. And so that's what we'll focus on in this talk. And we'll soon see phenomena that illustrate these phenomena for diffusion models. But the questions are salient for other generative models, like language models too. Now, to prepare us to discuss this relationship, I want to begin with a short crash course on diffusion models. I imagine many of you are already familiar with them, and so my perspective is a little bit different, and I'd argue simpler than the usual Markov chain or SDE formalisms. If you guys have perspectives of your own, I'd again love to chat about them later. But here's my take. So diffusion models are a class of generative models, which are algorithms that at the highest possible level take training data as input and then create new samples that are like their training data. Formally, we'll view our training data as samples from some complicated probability distribution, and the generative model's job is to generate new samples from that same distribution. Throughout this talk, we're going to use this abstract blue curve to represent the distribution from which we're sampling. I want us to think of points on this curve as representing data we'd like to sample, like images in this case. Representing data in this way as a low-dimensional manifold in higher dimensional space corresponds to the manifold hypothesis, which is a standard assumption in this domain, though we'll later see how we can relax this assumption to handle data that lies only approximately on a manifold. Now, in practice, we implement a generative model in two stages. In the training stage, we learn a function that stores information about the training data. For diffusion models, that'll be the score function of noisy training data, which we'll describe in just a moment. Then in the sampling stage, we'll use this learn function along with additional data like a text prompt or random noise to generate new samples. I want to now work backwards from sampling a diffusion model to explore the objects we're going to need and where they come from, both in theory and in practice. To sample from a diffusion model, we first generate Gaussian noise, and then flow that noise through a vector field that's defined via the score function of noisy training data. To obtain useful samples, the score function should be a vector field that points towards the support of the distribution from which we'd like to sample. You can see here how flowing points through this vector field would cause them to land on the blue data manifold. In practice, though, we train a neural net to approximate the score function by solving a simple regression problem called score matching. And this requires access to samples from the data distribution. Now, it turns out that it's easy to analyze score matching. It's just a simple regression problem. It has a single solution, which you can compute directly from the training set. And if you're worried about computational cost, we've also shown recently that it's easy to approximate. And so you might ask then, in light of this, why we bother with training? Why don't we just compute that solution and skip the training step altogether? And the answer, as we saw earlier, is that doing this would only generate training data. You can see how in this example, the optimal score points straight towards the red training samples. And since sampling ultimately flows noise through this vector field, those model samples must land at the training data. So this means that diffusion models succeed at creating new data, but only by failing to optimize their training objective. And understanding how and why this happens is the problem of generalization. Now, this paradox might lead you to believe that at the very least, diffusion models should depend strongly on their training sets in practice. In particular, suppose we train two diffusion models on disjoint data sets. It seems reasonable a priori to expect that each of these models would generate samples from different distributions. But even this turns out to be false. And in fact, my colleague Zara recently discovered that models trained on disjoint datasets can generate nearly identical samples. You can see examples on this slide where each row corresponds to a diffusion model that was trained on a different dataset. This second paradox illustrates the importance of data attribution because it shows how weakly a diffusion model can depend on its training data, more weakly than we'd expect for an optimal model, and more weakly, I'd argue, than our intuitions would suggest. So now that we're on the same page, we're ready to see how diffusion models depend on their training data. We're first going to explore how neural net smoothness bias can explain how diffusion models generalize for data that's supported on manifolds. We're then going to see how to relax the manifold assumption so we can handle data that lies only approximately on a manifold. And finally, we'll zoom into how a particular diffusion model is influenced by its training data, and we'll explore a sensitivity analysis framework that predicts how a diffusion model responds when you perturb its training set. I want to begin with an example. So suppose we have these 3 red training samples, and we'd like to use a diffusion model to generate samples from the blue curve on which the training data lies. Our first paradox was that the optimal diffusion model for this training set can't do that because its score function points directly towards the training data. We don't do that in practice though, right? Instead, what we do is we train a neural net to approximate the optimal score, and we get a vector field like this one, which points towards the blue data manifold rather than the red training samples. This is what enables our diffusion model to generalize. Now, in light of this, I want to compare the optimal score function and its neural approximation by plotting them side by side, and we'll see if there's any differences that jump out at us. So if we do this, one thing that immediately becomes apparent is that the neural score on the right is much smoother than the optimal score on the left. And this is especially clear if we pay attention to the pink Voronoi boundary between neighboring training samples. You'll notice that whereas the optimal score changes direction sharply as it crosses those Voronoi boundaries, its neural approximation remains smooth everywhere. Now, this seems intuitively connected to the optimal model's inability to generalize. Okay? Intuitively, those sharp changes in direction are what cause samples. Which,
I have
yes.
a question. So for diffusion model, like score matching models, the vector field depends on time step, right? So what time step is this?
So, right, that's a really good point. Throughout this talk, to keep things simple, I've been visualizing the score field at the very end of the sampling process. So this is in the low noise regime when you're close to the data manifold. You can prove that in that regime, the score should just become a projection onto the data manifold. Okay. Intuitively, those sharp changes in direction on the left are what cause samples, which are flowing through this vector field, to land on the red training samples rather than hit the blue curve. So the reason why I'm showing the last time step is that that's the time step that determines whether you're going to land directly at a training sample or somewhere else for the purpose of generalization. Now, all of this suggests a natural hypothesis, which is that neural diffusion models generalize because instead of learning the optimal score function for their training set, they instead learn a smooth approximation. This lines up with some well-known facts about neural nets, like their spectral bias towards learning smooth approximations of their target functions. We found evidence of this in a recent work of ours called closed-form diffusion models, where we characterized how smoothing the optimal score function impacts the model samples. In particular, we showed that if you smooth the optimal score function and then sample from the resulting diffusion model, those samples will interpolate between nearby training samples. Now, if the training data densely covers the underlying manifold, then these interpolants will be new samples that live near the data manifold, which is another way of saying that this model is going to generalize. This slide over here shows a simple example. Because the red points are a dense enough sampling of the blue curve, which is a very simple low curvature manifold, the smooth model samples in green approximate the curve pretty well. Now, of course, as you might imagine, the manifold geometry matters a lot here. And since we published this paper, there's a group at Oxford led by Tyler Fargo that has done some great work fleshing out precisely how generalization depends on geometric factors, like the smoothing kernel, the manifold's curvature, and the data dimension. Now, beyond its value for explaining generalization, we might wonder if we could sample with this smooth score. Remember, we could practically do that for the optimal score because it doesn't generalize, but we just saw in the previous slide that the smooth score does. And so we'll now see a two-step recipe for generating new samples that doesn't involve training a neural diffusion model. We're first going to approximate the optimal score, and then we'll do some cheap post-processing after the fact to smooth it. So to see how to efficiently approximate the optimal score, I'm going to take a look at its formula. So the optimal score for a finite training set is a sum of n vectors, each one pointing from the input C towards one training sample. This means that to compute the optimal score, you need to iterate over the entire training set, which, as you might imagine, is typically very large in practice. However, this sum has nice structure to it. In particular, it's a distance-weighted average of vectors pointing towards training samples, and it's often dominated by the nearest training samples to the inputs. We showed how to use this structure to build a simple and efficient estimator that uses only the nearest neighbors of the input and a handful of uniform draws from the rest of the training set. Now, this is great because approximate nearest neighbor search is a well-studied problem and an active field of research. And in particular, we've already got many efficient algorithms for nearest neighbor search, with new ones frequently being developed.
Does it matter what sort of feature space you do this nearest neighbor search in? Like, are you just doing it in terms of the pixels, or is it like some other lower dimensional feature representation?
So for the purpose of this paper, we did the search in pixel space. You're absolutely right that you'd expect that doing this in a latent space would allow you to pick up on maybe a more semantically meaningful notion of similarity. For the purpose of sampling, if you want to generate reasonable quality samples, you are going to want to do this entirely in a latent space. Because just thinking back to what the inductive bias of this model is, it outputs interpolance between training images. If you think about what that looks like, it's just a superposition of images in pixel space. And so you got to do this in latent space to get reasonable samples. Okay, now knowing how to approximate the optimal score doesn't get us all the way to a useful sampler just yet, because this will still output training data. We need to smooth it to generate new samples. Fortunately, though, this is the easy part. All we need to do now is average the optimal score over a small neighborhood of its input. And in practice, this just requires us to compute the optimal score a handful of times. So since we've already shown how to do this efficiently, we've got all the pieces we need for our sampler. And it turns out that running this sampler in the latent space of the right autoencoder lets us draw new samples from the target distribution without needing to train a neural diffusion model. This means that we don't need neural nets to generate new data. What really matters is knowing how neural scores differ from the memorizing optima, and then being able to simulate that behavior after the fact. Now, I found this project really exciting for a couple of reasons. One of the most important open questions in the theory of diffusion models is generalization. This project showed that we can learn about how diffusion models generate new content by studying how and why the optimal score, rather the score function that we learn in practice, differs from that optimal score that can only reproduce training data. I've listed a few candidates on this slide, and we'll say more about these towards the end of this talk. This also gave us a new two-step recipe for generating data without neural nets. First, efficiently approximate the optimal score for a training set, and then corrupt it after the fact to mimic a neural score. Now, you'll note that this recipe is completely generic. We can use any corruption we want as long as it's computable. And this means that the samples you get from this method should improve mechanically as we gain a better understanding of how neural diffusion models generalize, which is one of the primary goals of my research. So far we've seen how neural nets bias towards learning smooth functions can explain how diffusion models generalize when they're trained on data that lies on a manifold. This result highlights the importance of matching our inductive biases to the geometric structure of the data we hope to sample. And in this case, we were motivated by the manifold hypothesis, which is a very common modeling assumption in machine learning. But modeling assumptions are assumptions rather than facts about our data because they aren't always perfectly true. What we'd really like is an inductive bias that encourages diffusion models to generalize for data that lies only approximately on a manifold. And so to do this, we'll now derive a principal training objective that's robust to noisy data. We'll see how optimizing it naively will be intractable for real-world problems. And so in light of that, we'll see how to instead optimize an equivalent objective that's cheaper. More broadly, this section is going to show how matching our theoretical assumptions to deep learning practice can yield large benefits to practitioners. This section of the talk is based on our paper called Nuclear Neural Regularization for Deep Learning, which appeared in Neurips a few years ago. So in this section, we're going to slightly change how we parameterize a diffusion model. In practice, a diffusion model's score function is often parameterized by a denoiser. If the score is a vector which points from the input towards its projection onto the data manifold, then the denoiser is the function which computes that projection. Now, it turns out that denoising performance is closely related to generalization. In particular, if we have a denoiser that accurately reconstructs data from the target distribution, then a diffusion model built from that denoiser will generalize and sample from that distribution. And so in light of this, our goal is going to be to learn a denoiser that can only access data that lies approximately on a manifold.
This statement seems a little bit in conflict with this idea that if the model minimizes its objective perfectly, it doesn't generalize. You're sort of saying if it achieves low denoising error, which is the objective we're training it on,
Right.
then it generalizes. So how do I square these two things?
So if it achieves low denoising error on the target distribution from which you'd like to sample,
I see.
then it'll generalize.
Okay, gotcha.
That's the connection.
Not the training data.
Exactly.
Thanks.
Right.
Yeah.
Okay. I want to build intuition on a very special case of our problem. So suppose for now that we're dealing with a very simple instance of a manifold, just a low-dimensional linear subspace. Suppose also that we can only access data that lies approximately in the subspace, which we're going to model by adding noise to our data. Our goal is going to be to learn a denoiser that can recover clean data without ever seeing any, whether that be at training or at inference time. Now, this turns out to be a well-studied problem called unsupervised denoising. And there's a classical framework for this problem called singular value shrinkage. As its name suggests, this strategy shrinks the small singular values of the noisy data because these contain mostly noise when the underlying clean data is low dimensional. Now, this turns out to be a well-developed body of work, and there are optimal shrinkers for many classes of corruptions that go well beyond the simple IID noise that we've considered so far. Now, it turns out that in our setting, the optimal shrinker is a linear map that you can get by solving a particular optimization problem. There's a lot of math on this slide, so I'm going to spend a few minutes just unpacking this. So this objective is telling our solution to first preserve as much information as possible from the noisy data. That's the first term. In other words, it's a look like the identity function add noisy data. But you also want the solution to have low rank, which means that the solution is going to map inputs onto a low dimensional subspace. Because this is where the clean data lives, I think this is an intuitively reasonable objective to optimize. Now, the regularizer we use here is the nuclear norm, or the L1 norm of the optimal shrinker's singular values. If you're familiar with L1 regularization, then you'll know that it encourages sparsity. In this case, sparsity means few non-zero singular values, which is exactly the same thing as preferring low-rank matrices. And so everything lines up so far. Now, so far, though, this has just been a special case. Right? Remember that we're assuming our data lives near a nonlinear manifold, not a linear subspace. But the good news is that nonlinear manifolds locally look like subspaces, and nonlinear functions locally look like their derivatives, both of which are linear objects. And so we can very naturally generalize this shrinkage problem for linear data, and we get this objective on the slide, which is formally pretty similar to the one we had before. So this new objective still tells the denoiser to preserve as much information as possible from the noisy data, behaving like the identity of noisy data. But now the regularizer tells it to locally behave like a low-rank matrix. We're going to encourage this behavior by penalizing the nuclear norm of the denoiser's Jacobian matrix, which is just a high-dimensional derivative. Unfortunately, though, there are some critical computational issues with this strategy. So that Jacobian is going to be a huge matrix for problem sizes that are very typical in generative modeling. For example, if you're learning a denoiser for 1024 by 1024 images, it'll take up to 40 terabytes to store a single Jacobian matrix. And what's worse, computing its nuclear norm requires an SVD, which is a cubic time operation. So these issues would make it seem like this strategy is doomed from the get-go. Fortunately, though, we made a theoretical breakthrough that showed how to entirely avoid that costly regularizer by taking advantage of the structure that's shared by all neural nets. I'm not going to burn you with the proof of this theorem, which is pretty involved, though I'd love to discuss the methods one-on-one if anyone who's interested. Instead, I want to spend some time reviewing the critical assumptions that make this theorem go through and contrast these two equivalent problems. My goal in this section is going to be to convince you that beyond being a neat piece of math, a theorem like this allows machine learning practitioners to solve challenging problems that would otherwise be completely out of reach, regardless of how much compute you can access. So I want to start by taking a look at that first more costly problem, which I've mapped onto our unsupervised denoising problem. So over here, L is a continuously differentiable loss function that can depend on both the inputs and the outputs of the denoiser. That's not a very restrictive assumption. It includes many loss functions that occur in machine learning, such as the regression loss from unsupervised denoising. Now, we're minimizing the expected loss over some data distribution, like the distribution over noisy images and unsupervised denoising. And to encourage our solutions to map onto low-dimensional manifolds, we've regularized this problem with the Jacobian nuclear norm. As we just saw, solving this problem is going to be way too costly in practice because computing that regularizer entails taking the SVD of a gigantic Jacobian matrix. Okay, and our result is going to save us from having to do this very costly Jacobian computation. Now, to apply it, we're going to need one key non-trivial assumption. We're going to need to be learning a composition of two functions, which we've labeled H and G on this slide. The good news for us, though, is that this is exactly how neural nets are built up. If neural nets are compositions of simpler functions. And if your neural net has many layers, you can choose how to group them into H and G to apply this theorem. Now, this assumption is a little bit unusual in the theory literature. And that's because compositions of functions are often ill-behaved. If you want some intuition for that, think of how expressive a neural net can be. If you can express a very large class of functions, then you typically can't say a whole lot about it. This theorem is a notable exception to that pattern. And I think this suggests we've probably been leaving some useful structure on the table that might be useful for understanding how real-world generative models behave. Now, under this assumption, our result lets us solve an equivalent problem, which has the same loss function as the original problem, right? All we've done is reparameterize F as a composition of G and H. But it's got a different regularizer that'll turn out to make this problem much cheaper to solve. Now, that's not obvious at first glance. That second problem looks a bit more complicated formally. And so I'm going to break down how we compute each regularizer and show you how much faster the second one can be. I'm going to start by breaking down the Jacobian nuclear norm. So the first step is going to be to compute a Jacobian matrix. That's a matrix of partial derivatives that PyTorch can compute for you automatically. For high-dimensional functions, like the ones we typically see in deep learning, that's going to be large and very expensive to compute, but that's not going to be our main obstacle just yet. We'll see how to deal with that issue in a couple of slides. The next step is going to be to take the SVD of this matrix, and this is going to be the step that really kills us. So its complexity is cubic in the data dimension, which is often in the millions for data like high-resolution images. And so we're not going to be able to compute this SVD in practice. The final step will be to add up the singular value we just computed, which are just the entries of that second diagonal matrix. That's step CC. Now, on a small problem involving 64 by 64 images, this might take in the ballpark of 300 seconds on GPU. And you're going to incur this cost every single time you have to compute a Jacobian nuclear norm. That's not great. And so we're going to see how much better we can do using our result. So to compute our alternative regularizer, we now need to compute two Jacobians, one for each function in our composition with respect to its input. This is still going to be very expensive, but we'll soon see how to avoid these Jacobian computations altogether. In return for this extra Jacobian, though, we get a huge benefit, which is that squared Frobenius norms like these don't require any cubic time SVDs, right? The squared Frobenius norm of a matrix is just the squared L2 norm of the unrolled matrix. And to compute that, you just need to iterate over the matrix's entries, which is very cheap relative to an SVD. And so on the same small problem that we timed earlier, this is going to be roughly 2 orders of magnitude faster. That gap grows with problem size, and so this actually understates the benefit of our result for real-world problems. But like we saw earlier, just storing those Jacobians can take up to 40 terabytes each for realistic problems. And even when we can store them, computing the Jacobians accounts for nearly all of our runtime. So for this to be feasible in practice, we'd really like to avoid computing those matrices altogether.
I know you said that obviously going for the full proof is
Yeah.
but something we don't have time for, but can you give some intuition for why doing this composition allows us to turn a nuclear norm into 2 Frobenius norms? That feels like too good to be true, and I want to understand like why that works.
So to be clear, going back a second to the result, so what this result says is that the minima of these problems is equivalent. This is not a new identity.
The objectives are not the same, but
exactly.
are equivalent.
That's exactly right.
Gotcha.
If you want a bit of explanation for why this is true, I can tell you very high level. It's a generalization of a theorem for the matrix case that Nadi Strebro and John Rennie proved in the 2000s. That result is still pretty unintuitive, in my opinion. I think of it as like a matrix generalization of AMGM, but I'm still trying to wrap my head around like how to picture it. But yeah.
So suffice it to say, I'm not going to get an intuition in 2 minutes here.
It's a little longer than that.
Okay,
yeah.
fair enough.
Okay.
Do you have a question, Horace?
Yeah.
If you think of a function as an identity composed of itself, can you always turn the nuclear norm to Frobenius norm?
Right. So I guess the other catch over here is that the theorem we proved assumes that all your functions live in C infinity, and so you're optimizing over a fairly large function class. The theorem, the result also holds in practice for neural nets because they're expressive enough to give a decent approximation to C infinity. But if you were to like hard code G to be the identity and just learn H, this theorem wouldn't hold anymore. You really need to be optimizing over both function classes at the same time.
I mean, ReLU networks are already not C infinity.
That's true. So technically, you can't do this for ReLU networks. So in 2D examples, that distinction actually does matter. We found that like you can compute a simple 2D toy example where you know exactly what the solution of the first problem should be. And this result breaks if you use ReLU networks. The differentiability actually does seem to matter. However, you can use any other differentiable activation and the result holds really nicely, but there are limitations for sure. Okay, great. Okay, so the goal now is to avoid needing to even compute those Jacobians in the first place, because that's very costly if you have high dimensional inputs. And the good news is that this regularizer is easy to approximate using some well-known methods from the 90s that only require us to probe a function's values near a point. The intuition behind this result is pretty simple. It's basically saying the magnitude of a function's derivative is large. So on the left hand, that's what's on the left-hand side. Wherever the function's values are changing rapidly, that's what we're measuring on the right-hand side. Now, this approximation is very cheap. On this same example, it now takes less than a millisecond to compute this regularizer. And this is especially striking if we compare that runtime to the nearly 300 seconds we originally had to tolerate. That's a 6 order of magnitude cost reduction. And I think this is a great example of how carefully aligning our theoretical assumptions with real-world practice gives us theory that's not just interesting math, but also directly useful to practitioners. All right, so with this result in hand, let's circle back to our original problem. So using this result, we can now solve our unsupervised denoising problem to learn a very accurate denoiser that only ever sees noisy data during training, which is data that lies approximately on a manifold. Like we saw at the beginning of the section, we can then use this denoiser to build a diffusion model that generalizes well. And so a result like this one gives us a path towards generalization in diffusion models for data that lies only approximately on a manifold. All right, so far in this talk, we've been thinking about diffusion models as a generic class of models. In particular, we've seen how two inductive biases interact with the geometric structure of our data to enable diffusion models to generalize. However, if you're a practitioner, you're not typically thinking about diffusion models as a generic class. Instead, you have a particular diffusion model that's already been trained on some data, and you're interested in how your model depends on its training data. And to respond to this need, we developed a principled and tractable framework to estimate how a diffusion model's score function and the samples it generates respond to perturbations in its training data. To set up this work, I want to recall our two-stage description of diffusion models from the very beginning of this talk. Learning a score function in the sampling phase, in the training phase, and then generating new data with it in the sampling phase. Now, I want to think of training diffusion model as constructing a very special type of map, which sends the target distribution from which the training data are drawn to the optimal score function for that distribution. Similarly, I want to think of sampling a diffusion model as constructing a map from the score function you just learned to new samples from that model. Now, the overarching goal of my research is to understand how generative models depend on their training data. And so for diffusion models, which are characterized by their score functions, this means that we need to understand the properties of the training map. Turns out that we actually already know quite a bit about this map. In particular, we know that for any target distribution, there's a unique optimal score function. And so we know what values this map takes on. However, until recently, we knew very little about its derivatives. Now, these derivatives would tell us how an optimal score function might change as you slightly perturb its target distribution, which is a critical quantity to study if we want to understand how diffusion models depend on the training data. We recently showed that not only can we differentiate this map in principle, but that this computation is tractable for real-world diffusion models. This is pretty surprising, I think. In general, you wouldn't expect the derivative of a map from probability measures to vector fields to be a tractable object that you can compute and even visualize. But it turns out that because diffusion models have so much structure to them, this is actually the case for this, specific problem. Now, here's why you might expect this to be possible. So the optimal score function is a vector field that points towards the support of the target distribution. Since there's a unique optimal score for any target distribution, that map from target measure to the optimal score is perfectly well defined. It's a valid function. Now, if that map is also well behaved enough, we might just be able to differentiate it. The particular derivative we might be interested in is this map's directional derivative, which would tell us how the optimal score would change if we were to shift a little bit of mass toward the new distribution. In the real world, this would map onto adding or removing data from the training set. And intuitively, in an example like this one, you'd expect that vector field to shift away from the blue curve and towards the red point. Our key finding was that not only can we write down a formula for these derivatives, but that we can also exactly compute them in practice. And in fact, doing so requires only black box access to the original score function and its spatial derivatives. And remember, this comes from a diffusion model we've already trained, so we've got this. We also need access to the new samples whose influence we'd like to estimate. Now, I say influence here deliberately because our variational derivative is a generalization of influence functions for diffusion models. Yes.
Sorry, can I ask you a question? When you say black box and you talk about the derivatives, how might I get those?
So when I say black box access, I mean, you don't need to know what the model weights are. You just need to be able to query the score function at a particular input and its spatial Jacobian at that input. So in particular, you don't need to know anything about the training procedure, how you parameterize the diffusion model. Okay. We can do all this at fairly reasonable cost. It's comparable to a density query, which is a pretty common operation in this space. And as a result of all of this, we can now estimate how the optimal score would change if you were to shift some mass towards new samples or away from existing ones. Now, in practice, the score function isn't an end in itself. We use it to generate samples. And if you're a practitioner, you might be more interested in predicting how those generated samples would change if you were to perturb the training set. Intuitively, though, since the diffusion model generates samples by flowing noise through a vector field that's defined via that score function, if you know how the score function changes when you perturb the training data, that should give you enough information to predict what happens to the samples that have flowed through that vector field. And it turns out that you can do this using standard methods from control theory, which tell us how paths through a vector field respond to changes in the field driving those paths. And so by combining our variational derivative with these control theoretic results, we can predict how a sample that a diffusion model has generated will respond to changes in its training data. Now, so far we've developed methods for predicting how a diffusion model's score function and its generated samples change when you perturb its training set. But we can take this one step further, right? In practice, you might be interested in questions like what training samples are responsible for generating IP-protected content, or what new training data would encourage a model to generate samples from an underrepresented class. Because you can compose the sampling map with a classifier that measures attributes like these, this sensitivity analysis for diffusion models can serve as the foundation of a framework that can answer broader questions like these. Okay, and now I want to discuss the path ahead, some future directions I'm excited to explore. The central goal of my research is to understand the relationship between generative models and their training data. To do this, we need to answer two key questions. The first concerns generative models as a class. If we take their training objectives seriously, optimal generative models should simply memorize their finite training data and become very expensive and very useless lookup tables. In practice, though, this doesn't happen. Generative models can solve novel reasoning problems and generate photorealistic images that couldn't have possibly been in their training sets. We need to understand why generative models can produce new content rather than memorize their training data. That is the question of generalization. Now, knowing why generative models generalize is just the first step. When I interact with a generative model like a diffusion model, I interact with a particular model that was trained on a particular data set and whose behavior will differ from that of a different model that was trained on a different data set. Understanding how my model's behavior depends on its training data is the question of data attribution. And to fully understand how generative models depend on their training data, we need to address both of these questions. I want to begin by charting the path ahead for generalization. So generative models generalize because in practice, we don't build optimal models for arbitrary training sets like that optimal score function that we saw earlier. Instead, we approximate the optimal model by training neural nets by gradient-based methods, and we typically stop well before convergence. Our data is not arbitrary either. In fact, it's usually highly structured, and that structure is likely to play a role in generalization. And so generalization in generative models must arise from some interaction between the inductive biases of our neural architectures, the training procedure, and the data geometry. Now, that's a rich landscape of potential causes, and I've listed just a few specific candidates on this slide. Some of them have already been studied individually in the context of diffusion models, both by me and by my colleagues in the field, but there are many promising candidates that remain unexplored. And I think what we're really missing is a cohesive picture of how these factors interact to give us generative models that can create new data. Once we can understand how generative models generalize, we're going to be well placed to predict and promote generalization. And here's what I mean by this. So suppose you're developing a generative model for a new data modality, which a few years ago might have been 3D shapes or molecules. Now, right out of the gate, you're dealing with some fundamental challenges. So the first is that you typically don't have access to much data, especially since oftentimes you only start collecting that data once there's a clear payoff to it. There isn't a canonical architecture for learning from that data, like transformers have become for text. And even if you find a good architecture, you might lack a good training procedure for it. So you're going to spend a lot of your time in compute fumbling around in the dark for that match combination. However, if we understood generalization, then we can predict in advance whether a combination of training data, inductive biases, and training procedures would be compatible with generalization. And it would also give you guidance for how to best promote generalization if you can't directly control one of those factors. Typically, that would be your training data. Oftentimes, you got what you got. And so in this way, I envision research and generalization as being something that's beyond, that doesn't just have theoretical interest, but that would also benefit practitioners quite directly. I think Armin had a question as well. Do we want to do these questions during the talk or wait until the end?
Really, like your presentation.
Yeah, I've only got a few slides left, so we can defer that to Q&A. Okay. I finally want to discuss the path forward for data attribution. So far I've developed a sensitivity analysis framework for diffusion models, which allows us to estimate how a diffusion model and the samples it generates respond to infinitesimal perturbations in its target distribution. I think this is a useful foundational contribution, but there's still a lot to do before we have a complete understanding of how a particular diffusion model depends on its training data. I think the first important step is to develop benchmarks and evaluation metrics. And I think this is particularly important for data attribution because when your goal is to predict how a generated model changes after editing the training set, the gold standard baseline is to just retrain that model. But of course, this is prohibitive for real world models especially if you're working with academic scale resources. And so it'd be helpful to have tractable proxy metrics to accelerate our progress. We're going to next need to develop frameworks for data attribution that operate beyond the perturbative regime, in which we're making infinitesimal changes to the target distribution from which we're sampling. In practice, we're typically interested in the effect of large changes in our data sets. And while limiting our attention to small changes allowed us to build a rigorous sensitivity analysis framework, this opened up a gap between theory and practice that needs to be closed. Finally, once these pieces are all in place, we'll be ready to build a framework for targeted data acquisition. I think this is a really neat problem because AI practitioners currently spend billions of dollars per year acquiring training data, which is increasingly being created from scratch to be included in some generative models training set. Now, they make these investments because they expect new data to improve their model's performance in some way or steer its behavior. But there are typically few guarantees that that new data will have the effect they anticipate. And I think that further work in data attribution will help turn these expensive bets into strategic investments. For example, if you could accurately predict how a generative model's behavior would respond to a change in its training set, then you'd be able to decide whether to acquire a particular data set or to even predict what data you should acquire to steer a model's behavior away from something that's problematic and towards something that's a bit better aligned with user needs. All right, so with that, I'd like to thank you all for your time today. Aside from generative AI, I've also worked in optimal transport, 3D deep learning, and way back when on principal deep learning methods. So if any of that interests you guys, I'd love to chat about it. In the meantime, I think we have a few minutes for Q&A. So yeah, thanks for your time.
Hey, I had a quick question from earlier. I was wondering if the method that you outlined for kind of like training free synthesis of samples, like if you could use this to somehow predict the best possible network that you could get by learning on some data. Like what is the best you can do or best you can hope to do? Or is there still some gap between the samples that you can get from this training free method versus like a network?
Yeah, so that's a great question. There absolutely is a gap between the samples you could get from these training free methods and neural diffusion models. I don't pretend to have solved the problem of needing to train diffusion models. I do think the idea of using this as a baseline to benchmark our methods against is an interesting one. Some of my colleagues, like Mason Cam at Stanford, have conjectured different types of training-free models that rely on different inductive biases, like translation equivariance and locality for convolutional models. I don't think he's thought about or I thought about whether you could use that as like a benchmark to see how well you're doing with a neural diffusion model, but I think it's a really cool direction. I'd love to chat about it.
Sure. Yeah. Very cool. Thanks for the talk, by the way. It's excellent.
Awesome. Yeah, glad you enjoyed it.
Phil Klein had a question. Okay.
Hello. I think my question was pretty similar to the previous question, so I'm good.
Okay. Thanks.
All right.
You want to take one more?
Yeah.
Thank you for the talk. I thought the visualization with the blue line and red dots is very like intuitive.
I'm glad you enjoyed it. Yeah.
I'm wondering like if you could like share some like intuition on like what would the image look like when like it's slowly getting further away from the blue line? Like is it just becoming like a flat image like the noise?
Yeah.
Or also like what might the image look like when we kind of travel along the blue line, but between two like red points? Is it just like blending the two images? Like how might that look?
Yeah, so the picture I have in mind is that stepping away from the blue line is sort of analogous to adding noise to the image. You can think of sampling as slowly moving from like a Gaussian towards the data manifold. Now, in terms of what happens if we move between training samples on the blue line, I think really the key question in this analogy is whether you're moving in a straight line or along the manifold. A straight line interpolation would effectively correspond to like fading one image out and fading the other one in. This is not a very intuitive interpolation, and this isn't what you'd expect to happen if you travel along the blue curve, which to me is like a geodesic interpolation. So, you know, there are generative models where you can traverse the latent space between samples and get a much more intuitive transition between two samples. I think this is closer to what you might expect moving along geodesics on a manifold to look like. But I'm actually not sure off the top of my head if that connection is fully rigorous beyond just like the intuitive picture that moving in latent space is like moving along the data manifold.
Thank you.
Yeah, of course.
Yeah, I had a quick question. It's relevant to the slide that you showed with the smooth versus the 3 Voronoi cells.
Yeah.
Does that imply in any way that these networks are over smoothing and that we might get a better network that still has all the properties we care about of fast convergence and being smooth everywhere that has higher curvature?
That's a really interesting question. So I'd say the answer to that question is maybe, and I think it's architecture dependent. So I think this picture of, you know, neural diffusion models generalizing because of the straightforward smoothness bias is a good explanation of what happens in low dimensional settings. I think in higher dimensional settings, the question is a lot more complicated. Smoothness biases are certainly part of the story, I think. I don't think it's the end of the story because one of the things we show in this paper is that if all you've got is that smoothness bias, what your model will do is interpolate in some clever way between nearby training data. If you have a very dense sampling of the data manifold, that might get you close to something that looks like a real world sample. But you can imagine in pixel space what that might look like. You're just superimposing two images. And so I think you need other inductive biases to close the gap.
Isn't this equivalent to saying is my data manifold smooth?
Yes. So I think another way of looking at that is exactly right. Like the real world data manifold, to the extent we believe this exists, is very high curvature, very we don't, I think so. I mean, like, think about what happens if you take two even like similar images and try to interpolate linearly in between them. If their faces like very well registered, like sure, it'll look kind of face-like in between, but even there, I think the curvature is, you know, less trivial than you'd expect.
I think that's a good discussion for another time.
Yeah.
Let's let these good people go, and let's thank Chris for the lovely.
Yeah.